All right, so I am a PhD student at the University of Alabama in Huntsville. There's a lot that goes into that. It's a very difficult thing for me. I'm studying under Dr. Jason Casabry. Really fun. The other day, someone from the university reaches out and they said, hey, doesn't your student Destin, doesn't he like do talks occasionally or whatever? It was the American Astronautical Society. This is a group that discusses the future of space exploration. Aerospace CEOs, industry leaders, students, government officials, they've been having these discussions since the 1950s. They asked if I would do what I call a talkie talk. Now, usually I say no to talkie talks because I like to prepare and get it right, and it just takes a long time. Plus, I only do a few of those a year, and I just didn't know if this was the right thing to do. But the more I got to thinking about it, the more I realized that the people that were going to be in this room are the movers and shakers in the aerospace industry. And these are the people that are doing things like planning the mission architecture to go back to the moon. And when I looked at the name of the talk, it was Advancing Space from LEO to Lunar and Beyond, or at least this is the symposium. It's the 2023 Von Braun Space Exploration Symposium. Now, Wernher von Braun, or von Braun, depending on what way you pronounce his name, was the main architect behind the Apollo program, which is when we went to the moon. Right now, America is doing what's called the Artemis program. And the Artemis program is our effort to go back to the moon to take humans there now with new technology. It's very interesting. With most talkie talks that I do, I like to provide an external perspective to the organization or the company that's asked me to come in and speak. And in this case, all the people in front of me are the most important industry leaders in aerospace. And so I thought about what it would look like to take a third-party perspective view of Artemis. And I thought that would be pretty good. But the more I started digging into Artemis, the more I realized there might be some issues in how people communicate about it. Like there's some architecture problems that people are unwilling to talk about these days because of how they got there politically. And I was like, you know what? I just want to go say the thing that nobody's saying. So that's what I decided to do. Now, a lot of people I respect, when I was doing my research and asking these questions, they said, be careful, Destin. If you say certain things, this might change your relationship with NASA forever. And I thought about it and I decided, you know what? This is the truth, and this is what needs to be said, and NASA, please don't hate me. In all seriousness though, I'm nervous about this talk before I go in. You'll see that, and I decided just to play the talk for you and let you see what this is like. Now, to be clear, being a YouTuber means nothing in this room. So the first part of the talk is me trying to establish credibility within the aerospace industry by saying some of the things that I've done. I've done the Defense Acquisition University. I know what it means to like develop a system that's going to be human rated. So I have to like establish that, but also I have to sprinkle in a little of the, just I'm the YouTuber guy who you think I am. And then in the end, I want to ask the difficult questions. So for me, this was an exercise in something called rhetoric. Rhetoric is trying to persuade somebody to a certain position, and that's what I was doing here. So I thought you would enjoy being in the room. This is me in a room I usually wouldn't get to be in, and I thought you might like to peek in on this and see what I had to say, and I would love to know what your thoughts are with my points about Artemis. So that's it. We'll see how it works. I almost forgot. At some point, I'm going to show you this year's sticker design for Patreon. If you're interested in that, I think it's really cool. So I'll show you that here in a bit. Anyway, on with the talk.
We now get to our closing keynote for the day. We are really honored and pleased to have this speaker with us. So he's no stranger talking to large audiences. Destin Sandlin is a husband, father, and aerospace engineer known for his educational video series, Smarter Every Day. He's also a current UAH student. So Destin, I turn it over to you for your talk. Thanks.
Hello. I'm seeing people I know. That's always good. And so my name's Destin, and when you leave here, what I'm hoping is that you'll look at the mission differently. In a world of talkers, you'll be a thinker and a doer, and ask the hard questions. And I've kind of, let's just do this. Who is this dude? All right. So it's a thing we do in Alabama. I know you guys are from all over the place. So here in Alabama, we like to just. Can you hear me? Is this good? Okay. Here in Alabama, we're just kind of low-key rednecks. You know that about us by now, right? So I'll just kind of go through who I am. So I grew up across the river, and just a redneck kid. That's me and my big dog, Thunder. My dad's over there. Dad, you can come up here and sit down if you want. You're okay? Yeah, Dad's here. So Dad's awesome. Yeah, and So I grew up just a normal kid, and my grandfather, my dad's dad, worked at this little outfit called the Army Ballistic Missile Agency. Have you ever heard of it? Yeah, you heard of it? Yeah, it's pretty good. So his name was Pryor Wilson Sandlin. Why do people always laugh when I show this slide? Every time I show my grandfather, they're like, ha, ha, ha. I was like, I don't understand. This is how I grew up. It's a culture thing, I guess. But my grandfather, the same guy that taught me how to shoot a squirrel out of a tree, the guy that taught me all kinds of stuff. I mean, he taught me about science, and he would take me outside, and he would show me stuff. And I remember Granddaddy didn't, I don't know if you remember this, Dad, but Granddaddy didn't tell me he loved me. He didn't say that. He said, boy, I love you to the comet belt. And I was like, what the heck does that mean? I don't know what that means. And then years later, I was sitting here in the halls of UAH, pencil whipping some stuff, and I was calculating the Delta V requirements to go to Mars. I was like, not only is it possible that we're going to go to Mars, it's going to happen. So he loves me out beyond that. I know this is the asteroid belt, not the comet belt. I have to say this because you guys are smart. But Granddaddy used to say things like that. And so the same person that made me feel really, really small and made me want to outwit a squirrel was the same guy that made me think about how big the universe was. And it's just how we grew up here in Alabama. It's great. I love it. So I went to University of Alabama. I learned a lot from Darrell Sandlin right over there, who worked on the James Webb Space Telescope. That's a picture of Dad when he was doing metrology on the sun shields for the James Webb Space Telescope. Really cool stuff. So Dad used to moonlight as a CMM operator and programmer, and he used to teach me stuff about coordinate transformations before I knew what algebra was. And so, yeah, I had a really neat upbringing. So I had internships at the University of Alabama. I worked at Eaton Aerospace. And the cool thing about that is the test cell next to me, I was working on the Joint Strike Fighter's fuel pump, which was also the hydraulic pump, really neat thing. So I used to test lubricity on that thing, but in the cell right next to me was the SR-71 fuel pump test cell, and it was designed to explode. And they told me there in Jackson, Mississippi, they said, yeah, so these dudes showed up, and they're like, all right, we need a fuel pump that needs to do this flow rate and this pressure. And the Mississippi boys were like, nothing needs a fuel pump like that. And they're like, build it. That's the coolest story ever. So anyway, I also worked at Little Debbie Snack Cakes. Basically the same level of, why are you laughing at me? Little Debbie's awesome. Let me tell you about Little Debbie. So imagine this is a sheet of zebra cakes right here. It's moving along. And you have a double guillotine striking that thing as it moves along. That's great. How do you get the chocolate drizzle on there? You just flip on this little switch and a little motor starts turning and the chocolate drizzle starts coming out and you get a sine wave on top of your cakes. But wait, there's more. Flip another mechanical lever, you throw in the cosine, you get it, out of phase. It makes a circle. That's how they do the fancy cakes. They do zebra cakes and fancy cakes on the same line. It's incredible. I'm wasting time. Let's keep going. So that was where I met my wife. Check this out. Isn't she hot? And my wife's really pretty too. You see my wife? It's great. So my wife and I, we have 4 kids, and we love them, and we think we're going to keep them. Right here, this is kind of my upbringing as a professional. I worked across the interstate here at a place called Redstone Test Center. That thing on the left is a component for something called an active protection system. So we were trying to defeat rocket-propelled grenades as they were fired at vehicles in Iraq and Afghanistan. I spent a lot of time on that, and maybe in 25 years we can talk about that. But it's really cool. On the right, I worked missiles for a long time. On the right, I went after a while, and I was like, I'm going to go work on aircraft because I don't know aircraft. I can't speak that language. And I learned a lot there. The cool thing about ATEC, Army Test Evaluation Command, we were in the Developmental Test Command. We were helping acquire material for the Army, material that would be used by soldiers. And so human rating of products was huge. I had to go through what's called the Defense Acquisition University. So I get what it's like to human rate a product. It's a big deal. And so I'm just kind of giving you that to say like, yeah, YouTube guy, haha, funny. Also, a little bit of experience in the field here. This is a cool thing. So this is what we would call at the range Tuesday. So a lot of people don't know we test javelin here. And I remember I remember a very specific moment. We had just blown up a Russian tank, and I remember the smell. I remember a lot of things. And we've gone down, and I'm living my best life, scoring the target, looking at the shape charge penetration in the hull. And I look at Tracy Williams, who's a Vietnam veteran, who helped develop Javelin for when it was called AWSM, if you know about that. So he helped develop it. He fought in the Vietnam War. And we're driving back up that road right there, Centerline Road, Test Area 1. And I look at Tracy and I said, Tracy, what are we doing? Like, what are we even doing? He's like, what do you mean? I was like, dude, we can destroy a tank. It's unbelievable how good we are at this. We can blow up tanks and throw the turret. There is never going to be another land war in Europe with tanks. This is dumb. Nobody's ever going to do this. Young buck, right? I got it figured out. I look at the graybeard. Tracy says, I've seen a lot of things. You never know. You never know, young man. Keep driving. Fast forward to recently, right? I think about that conversation a lot. I had it figured out. We got the new technology. There will never be these old problems coming back. Man, I think about that a lot. I used to goof around at night, making stuff in the garage. This is the first photo I ever took of a bullet striking a match. I was really excited about that. And then one day I did something silly. I got my dad a Father's Day present. And I don't know if the audio is working here, but we're just going to roll with it. So I uploaded this.
Hey, it's me, Destin.
Can you hear that at all?
I got my dad
Okay.
a present for Father's Day, and it's kind of weird.
So I uploaded this to the internet, and I was taking guidance and control classes here. And so I got him a chicken.
It's a chicken. I got my dad a chicken.
And I started looking at it, and I was like, there's some GNC stuff going on here. Like it knows where its head is, and like as it moves, it's somehow, there's a control loop here. And then this happened.
Motion is going, so you can compensate for it. But chickens are really good at this. So I'll show you. Watch his head stay totally stationary.
Right?
His body.
And you guys are super nerdy, so I know where your brain's going right now. You're going to the pigeon-guided bomb and world. I know what you're thinking. You're great. You're smart. But this is not what I was thinking. In the moment, I was like, I'm going to upload this to the internet because it's amazing. This is amazing because like there is clearly a closed loop control system here that appears to be optically coupled to this chicken, and it has. I'm back driving its spot. You know why chickens do this, by the way? Do you know this? This is like the smartest room I've ever talked to. Nobody knows this? Okay, so basically there's this thing called the vestibulo-ocular reflex. Do you know about it? Everybody look at my hand. I'm going to move my hand. Track my hand. Okay, birds have a hard time doing that. What they do is they lock their head, and that's their reference frame. And then they walk under it, and it ends up looking like this. So they'll walk, and then they'll walk under it. And they'll throw their head, and it makes sense now? That's what they do. And so, yeah, so whoops. That's great. So basically what's happening is I'm uploading this to the internet, and I'm like, man, I'm in the thinky place. I'm really smart, and I'm proud of myself for how smart I am. And then what does the internet do with this? Hey, look at this redneck playing with a chicken on the internet. He'll take that thing and he'll move it like this, and that head stays right there, And I'm like, no. I'm smart, I promise. I'm trying to be smart about this. They're like, no, man, that chicken wiggles so weird. And I was like, not like this. But then after that, something happened. I got to thinking about things. This grew into Smarter Every Day, and the reason it grew into Smarter Every Day is my dad made me take a business minor class. Honestly, that was part of it. But one of the things I did is I reevaluated how I looked at how I communicate with people. And basically, I decided, you know what I'm going to do? I'm going to do this. I'm going to take my videos, which I create, called Penny Whistle Productions. I'm going to brand it because Dad made me take a marketing class. I'm going to call it Smarter Every Day, okay? I'm going to focus on quality over quantity, and I just basically engineered it. That's all I did. And this happened. This is another thing I did. I said every video I make, I'm going to be deliberate about how I execute the video. I'm going to start the video with incredibly high personality. It's going to be fun. I'm going to tell you about chickens, and you're going to like it because chickens, right? And then slowly I'm going to ramp down the personality over time, and I'll ramp up the topical complexity. And when you ramp up that topical complexity, then people walk up that mountain with you, because it's not like, hey, 0 to 100 instantly. Let's talk about the sheer, let's talk about Moore circle right now. No, we're just going to slowly ramp up the mountain together. And then towards the end of the interaction, I ramp down before people get bored and scared. Kind of like right now, it's kind of getting weird right here. I kind of ramp it down, and then we land the plane. I was like, I'm going to do that with my videos. And it worked. It worked very, very well. And that was really, really cool. So if only going to the moon were that easy. Let's just get a plan. Let's just write it down. Let's award some contracts, and let's do it, right? If only your job were that easy. Why is it so difficult to do what you do? So my assumption here is that I'm talking to a room full of policymakers, intelligent people that are going to shape the future of human spaceflight. Is that correct? Somebody talk to me. Engineers, program managers. Yeah, this is the event where you get to put on literally your fancy pants and come hang out together, right? Yeah, I heard about the ball or whatever you guys did. Yeah, very nice. Yeah. So one of the reasons why things get difficult is politics, right? Politics. I learned this firsthand. You remember where this started, by the way, the chicken thing? Well, somehow it ended up here. Don't know how that happened. Somehow it ended up here. And what I learned in this moment is here in Huntsville, I was like, hey, I'm going to go talk to the president. Hey, John, what do you think I should ask the president? I get like 3 questions. What should I ask? John's over there. He's like, I'll tell you what I'd tell him. I'm like, yeah, what is that? He ain't going to take my guns. I'm like, John, here's the deal, buddy. This is literally going to happen. I'm literally going to talk to the president. I don't think I'm going to win friends and influence people if I do that. We got to that's not going to work. Politics, you got to communicate, right? So one of the things I did, I'm going to burn this because of time too. One of the things I did is I talked to him about political discourse. You know what? I'm not burning it. Let's go. Let's see.
I decided to ask the first question on how he gets smarter on topics he might not be the expert on. It was an interesting answer because it's clear that he's changed his methods over the course of his presidency. As he was answering this question, it was pretty clear to me that he was in interview mode. His body language was a little rigid. Now keep in mind that at this point, the president still doesn't know what kind of interviewer I'm going to be. For all he knows, I could be hostile. What happened next was a moment I will never forget. I knew before he did that we were both on the same wavelength, and I really wanted to let him know that. After all, I had listened to him already for 10 hours via audiobook. If you watch the president's face, you can see the exact moment that we connect.
And that, I think, is pretty consistent with how scientists approach problems generally.
Now, I actually knew that about you because I've listened to your audiobooks. And in Dreams of My Father, it ended with the 2004 Democratic National Convention speech.
Right.
Did you see it? Let's back it up and watch his body language. He's a little guarded, and then the connection. Isn't that cool? It's the exact moment that this quit being an interview and became a fun, intelligent conversation between 2 individuals who want the best for each other. It was a really cool moment, and I won't forget it.
Okay, so the president went on to explain some really interesting things, and he talked about negative feedback and how we as a society have lost the ability to provide negative feedback to each other. Because, why? Yeah, you guys are, so this is the thing. You're scared to even talk right now. I'm not joking. You're terrified to talk right now. And that's a problem. That's a problem. You know the truth, and you're afraid to say it. I'm Destin. Have a good day. No. The deal is we know things and we're afraid to say it. Why is that? Because we know the other side's going to fight, or we might get canceled, or whatever's happening today in your office. I totally get it. But we're engineers, right? Engineers know what this is, don't they? Young engineers on the front row. What is this? PID control loop. Rock and roll. That's what I'm talking about. What's an important part of the PID control loop? Let's ignore the letters. Let's go up here to the little summation symbol on the top right. You got a plus and a minus. What does that mean? Feedback. Right. Feedback is important to any engineer. If you have only positive feedback in the system, what happens to it? It goes unstable. Is this political science? This is math, right? Also works with political science. So, but it's really interesting. If you don't have positive and negative feedback in any system, it goes unstable and chaotic and things explode and break and it's bad, right? We know this to be true because whatever your degree is, okay? So I think it's important for negative feedback. So I'm grateful that I learned that. I also asked the president about his plans for deep space exploration at the time. Personally, I'm going to say this because it's an opinion I have, and I'm allowed to have opinions. I was unsatisfied with his answer at the time, okay? Now, that's a big deal because as people that work with NASA, you're an executive branch thing, right? So that stability in your direction is very, very difficult, right? It's hard. Congratulations, you guys have successfully navigated that. You have. There's a lot of reasons you navigated that. Artemis branding was a big part of that, kind of like Penny Whistle Productions flipping it to Smarter Every Day. It's great. I love how nervous you guys are. This is great. This is more fun for me than it is you. Everybody, I'm seeing this. I'm seeing this. Seeing this? This is so good. We're going, right? I've seen the video. We are going. I've heard people make fun of the video, but I think it's a pretty good video. Pretty good video. But there's this thing in the back of all your heads. At least it would be for me. The beautiful thing about this is I get to leave and I'm not in anybody's food chain in the room. That's the coolest thing about this. There's a scoreboard that exists, and the scoreboard looks like this. My buddy Michael made this today. It's a scoreboard, lunar landings, Apollo-era engineers and infrastructure, 6 lunar landings, Artemis, 0. That's pretty cool, isn't it? That's pretty cool. We made that. I was like, I bet that'll work. So we made that. So let's look at this. Let's look at this. So they did it, right? They've got points on the board. They did it. We're going to do it, right? We're going? We're going, yeah, okay. Let's look at how they did it. So this is a really cool graphic. This is the mission for Apollo, okay? Left Earth, circularized, left, went out to LLO, went down, ascent stage, come back up. You know, there's some rendezvous action in there. Come home, right? That's what they did. Here's Artemis 3. Let's look at this. Remember the part about saying the truth earlier? What do you guys think about this? It's different. A very wise, politically savvy engineer that I happen to know. So it's different. It is different. Why is it different? Why is it different? Okay, so let's zoom in on this one thing. Again, I'm going to leave the room. I can do that. You have to deal with this. So this is the orbit around the moon. It's not a low lunar orbit. It's NRHO, near rectilinear halo orbit. Have you guys researched NRHO? Have you looked into it? Do you know why we're doing it? Do you know why we're doing NRHO? Line of sight with the Earth. Okay, so Gateway. I know the reason. I know the reason, and you know the reason. A lot of you know the reason. If you don't, you need to figure it out.
Okay, so my tone when saying that is a little off. You probably have never heard Destin talk like that. Let me explain what's going on. There's a lot of people in the room, not all the people in the room, but a lot of people in the room understand that I am bringing up a truth that they've often wondered about. Why are we using NRHO, near rectilinear halo orbit? Because that's a really big orbit that takes many days to get back to the moon, whereas Apollo did low lunar orbit, which comes down really close to the surface of the moon. It's much more simple. So the reason we're doing this is because the Orion spacecraft does not have enough delta V to get down into low lunar orbit. It's just not how you would design the system if you were to design something from scratch. And so I'm saying the truth, and everybody in the room is like, he's saying things we don't normally talk about. And so that's why the tone is a little off. There's a lot of people in the room that this is resonating with, but that's what's happening.
So yeah, line of sight with the Earth is one of the stated reasons. So this was one of the charts that went into the decision-making process for NRHO, okay? So if you look over here, you'll see that for communication, I don't have a pointer, but you're smart, you can figure this out. So we've got Earth access, Orion, lunar access to polar low lunar orbit, station keeping, crewed spacecraft communication, and thermal, okay? So we're gonna put gateway there, and so contact with it via radio is important. So NRHO is, we're putting that there because we have to communicate with a crew, right? Right? I don't believe you. All right, so another thing they said is, you know, if we do this, then we can get down to low lunar orbit in half a day burn. This is the report. This was a NASA paper I read. It takes half a day to get from NRHO to low lunar orbit, right? Right? Guys, are we going? You should know this. You should know this. And that's kind of what I'm doing. I'm just going to tell you the trick. I'm going to be the bad guy for a little bit, and then I'm going to come back around and I'm going to inspire you at the end. But I just need to be the bad guy for a little bit, okay? Can you just roll with me on that? So here's the deal. This paper, which was used for justification to select NRHO, said it takes half a day to get from NRHO to LLO, right? What's the period time of NRHO? It's a week, 6.5 days, right? So what we're saying is we're in NRHO. The microphone is now the moon. We're in NRHO. It's a very high elliptical-looking non-Keplerian orbit. It's a 3-body orbit, by the way. It's a complicated thing. And so it's a thing, and it takes 6.5 days to get back by the moon. And when you do it, you're screaming. You're going fast, okay? Yeah, it takes half a day to get from NRHO to LLO if you're in the right phase. Because if you go try to land, and you're like, oh snap, we got to abort, we got a helium leak, depending on how far down towards the lunar surface you went, you might not be able to catch the bus. You might have to wait till it comes up back around. That should go in your mission planning. That dictates all kinds of things. That dictates, the man that taught me systems engineering is right there, Dr. Thomas. How you doing? He taught me systems engineering by talking about the transmission in his old truck. Is that thing running, by the way? Not yet. It's kind of like, well, never mind. So basically, you have to factor in everything. You have to factor in absolutely everything. So when I understood this, I was like, wait a second, are you telling me that it's possible that an astronaut could be on the surface of the moon, and whether it's a medical thing and the astronauts are smart. They know that if there's a medical incapacitated crew rescue mission, it's probably a body recovery. They're not dumb people. They know the risk. They are smart. So if something like that happens, how do we get them off? And the answer is it a half a day? It's not. We have to wait. So anyway, you need to know this. So anyway, when I started reading this, I started saying, they wanted NRHO to work. And so I came in here a little pious, like I sound right now. Remember, I'm the bad guy right now. I'm going to turn it around. So I came in like really wanting to punch you guys for making this choice. And then I started looking at the whole system. And I was like, oh, Orion can't get to low lunar orbit. We have to do this. It's not about communication. We can put communication on there to give us a green box to make it, to justify it. But what this thing doesn't say is that orbit can't see the landing site, but 86% of the time. So we're going to have a relay satellite no matter what. We're going to have a relay system. Because what's 14% of 6.5 days? It's about a day. There's a day that we're not going to be able to talk unless we have a relay satellite. Okay? So I got to think about all this. I found this in a paper. I thought this was really, really interesting. And then I started trying to understand the architecture to get there. Okay? I did not understand until this week when I really thought I was going to embarrass myself in front of you guys and then decided to further embarrass myself in front of you guys. I didn't realize that in order to get the human lander to the moon, we have to launch a bunch of additional rockets to tank up in low Earth orbit. I didn't know that. And I'm like, well, how many rockets do we have to do that with? And they're like, 6. And then I start, because I know people, I start calling people. I was like, dude, really, how many rockets is it? They're like, well, boil off. And okay, so I was like, some people were like, well, it's looking like 8. I was like, 8 rockets? We have to fire 8 rockets to fire 1 rocket to the moon? And then they're like, I mean, that's what they're saying, but it's probably more like 12. Really? And then I was like, I'm an engineer. I know how to do this stuff. So I started to account for like nominal schedule slip and boil off. And this is how many rockets it's going to take to fuel up that thing to get it to the moon. I've done the math. If you had any questions, I'm joking. Remember, I'm the bad guy. I'm going to turn around and be the good guy in a minute. So the question is this smart? And now's the time where people are scared to talk again. Not efficient. It's not efficient. So in the bottom right, I've drawn a picture. I've picked a picture from the We Are Going video. That's how many rockets went to the moon and landed for Apollo, for all of Apollo. And I'll take you back to this chart. Okay, I've said enough. Is this the simplest solution? Okay, so I should probably leave now. I'm Destin.
So it kind of looks like I'm picking on number of rockets in the talk here. I'm actually picking on communication. So the thing that's interesting to me is that people in the audience did not know the number of rockets that were going to be used to refuel the lander. That's a problem. I was trying to be funny, and there were stakeholders in the room. When I said 12 rockets the way I did, they laughed.
It's probably more like 12.
There are others that weren't laughing. Here's the deal. People didn't know the answer to this question. Shortly after delivering this talk, we saw an answer to this question. This article came out. Someone at NASA said it's going to take at least 15. So we at least have a baseline now. We have a floor. It could be more than that. It's at least 15. We still don't know the answer to how many rockets it's going to take to fuel that thing up. And I would submit to you that that's a problem. This is indicative of a communication problem. The fact that we have this very complex architecture and we don't know the exact answer to such a big question is pretty damning, because if we don't know such a simple answer to a big question, what does that say about the little things? Like when my grandfather was sipping coffee out of this mug down the road, they had quarterly reports on every little component of what was going on, down to the pressure transducers at some subcontractor at a small plant somewhere in America. They knew what was going to happen, because the more complex a system is, the more communication you need to make it work.
Saturn V Quarterly Film Report number 7.
Saturn V Quarterly Film Report number 9.
I think there's a problem, because right now we are 2 years out from this launch and we don't know the number of rockets. I don't think that means we're going to launch this thing in 2 years. I'm just saying it. That's where I'm at as an engineer. It's time to be honest. As engineers, we are not known to be effective communicators. That's just not a strong suit of an engineer. It is time to lay out and systematize the communication so that every organization that's involved knows far more information than they need, and we have actual targets and dates that are actionable, and they don't depend on a miracle in technological innovation occurring at some point on the Gantt chart. We actually have actionable things that have to happen in certain time frames. And if something doesn't happen, a critical technology isn't developed, we communicate that there's a schedule slip to everyone. The fact that it still says 2 years till this launch tells me that we have a communication issue, and I would like for that to be resolved by centralized leadership. There, I said my thing. Okay, so at this point, you will see a shift in the tone of the talk. I've kind of laid out the problem. Now I'm going to transition towards aspirational goals. Like, how do we get there? And it's going to hinge a lot upon this, what made Apollo a success, and you'll see me talk about that later here in the talk.
Remember what I said earlier about the importance of negative feedback. I am but a simple redneck Alabama engineer, okay? But for real, here's the deal. We're going. We've selected this architecture. So how do we make it work? I'm going to accept the contracts are written. We have European partners that are building the first node for Gateway. I'm going to accept it right now. Let's say everybody in the room accepts it. We're going to be unified, and we're going to make it happen. Now, what do you do with that information? What do you do with that information? I think the key is to learn lessons from the past, okay? Who is this person? Joseph Shea. He's a very, very important person. And this story I'm about to tell you is sad. Joseph Shea is sitting in a meeting here in the 60s in a presentation. If you're in the aerospace industry, you're in meetings all day long. That's what you do, right? That's what this guy's doing right now. Who are these people? Apollo 1. Yeah, there's a high school here in Huntsville named Grissom, after the gentleman on the left there. So these astronauts were getting ready for Apollo 1, and they knew there were problems with the capsule. They knew this. And the engineer team knew there were problems with the capsule, and everybody was working feverishly to figure it out. Everybody was trying to figure this out. And then on January 27th, 1967, a travesty happened. There was an accident on the pad. The capsule burned because they were in a 100% oxygen environment. A flame started by Gus Grissom's seat. They died. I remember being at a family get-together years ago. My grandfather, worked over at NASA, and I remember hearing the old-timers talk about that fire with deep sadness and reverence. And it occurred to me that something changed about NASA in that moment. Like, it changed. In the middle of Apollo, things were going like so fast, something changed. As a joke, I did not know this, and I'm just telling you this not to bring the room down, but I just want you to know that this happened. As a joke, at the end of one of the meetings, the Apollo astronauts, they talked to the photographer. They're like, "Hey, we got to do one more joke. We're gonna play a joke on Shay. So we want a picture of us with praying hands around our capsule, and we want to say," and they said down there, on the note, they said, "It isn't that we don't trust you, Joe, but this time we've decided to go over your head." They were jokingly saying, "We all know there's problems here, and we're not feeling good about it." At the same time, to be clear, the Apollo astronauts, these gentlemen, they knew the risk, and they didn't say something to the point where they're like, "We got to fix it." I don't know what happened. I don't know what happened. All I know is that an engineering mistake happened. And it wasn't caught. And that's going to happen because we're humans and we're imperfect. But when that happened, what I do know is NASA changed completely. The way they did things, like there were conversations that happened, and I'll go through that here in a minute. So here's something to think about. You guys like movies? Back to the Future, it's a pretty good one, right? Marty McFly, it's great. One of the cool things about those time travel movies is they'll go back in time and they're like, "Oh man, I can't change things because of how crazily I will influence the timeline of the future. Like if I move this bottle and the wrong person, whatever, like I might not even be born." Like it's so, these little changes have monumental impacts, right? By the way, a really good time travel movie, if you haven't watched it, Primer, really good. You've never heard of it. Budget for that movie was $7,000. Watch Primer, it's amazing. Great plot. So these time travel movies, they can teach us something, right? So why do we not realize that we have that much control over the future now? Like right now, you have that much control over the future as you're sitting there. Oh man, if I were just to send this email and say this thing in a compelling way and impact the way the program reviews go, and or CDR's coming up. If I could just get them to understand that ECLS needs to blah, blah, blah. Why don't we have that level of gravitas to what we think about now? I just think that's cool, something to think about. Has anybody ever heard of this document? Don't raise your hand. So does everybody remember the scoreboard earlier? Okay, so if I'm not mistaken, this room is full of people that are industry leaders that are in charge of taking humans back to the moon. Okay, in your head, don't raise your hand. In your head, answer the following question. Have I read NASA SP-287? The title of the document is, "What Made Apollo a Success?" Have you read it? And if you have not read it, I'm not joking about this, shame on you. Seriously. You have a whole generation of engineers that did the coolest thing engineering humans have ever done, and they gave you the playbook. They wrote it. All you gotta do is read it. I've read it. I'm not even in your food chain. I read this thing. Granted, I read it really, really fast so I could say I read it for effect. But I read it. And I made highlighting things in here. And I want to go through some of this with you. Imagine the scoreboard. You've got the people that actually went to the moon. If they handed you the playbook and they're like, "Hey, this is how you do it. This is the key." It seems pretty important. this exists. And it's crazy that you don't know that if you don't know that this exists. Okay, it's really fun to read, by the way. So it's written by several people that were over different things like trajectory calculations. Gene Kranz writes a section. It's a lot of really good stuff, but let's just read some of them. Of course, the way we got this job done was with meetings. Big meetings, little meetings, hundreds of meetings. The thing we always tried to do in these meetings was to encourage everyone, no matter how shy, to speak out, hopefully, but not always, without being subjected to ridicule. We wanted to make sure we had not overlooked any legitimate input. That's how you feel now. But I don't know, a lot of people are scared to talk today. It seems like they might have had a little different culture. All right, so spacecraft design. I thought this was interesting. So it talks about how a spacecraft, designing it, you have elements of missiles and aircraft. I've never designed a spacecraft, but I've worked with both aircraft and missile design. So I feel like I kind of get that. It says, and this is key, please hear this. This is the key to how to build your spacecraft. Build it simple, and then double up on as many components or systems so that if one fails, the other will take over. Examples are ablative thrust chambers that don't require regenerative cooling, hypergolic propellants that don't require ignition source, 3 fuel cells, and it goes on and on. I was kind of blown away to learn that the ascent stage in the current design does not use hypergolic propellants. That blew my mind. I was like, wait, so we're going up there, and we gotta ignite this. I get it. You want to use in situ and you want to do methane. I got it. Understand. But hypergols always work. You make them touch and they go boom. That's how it works. And so I just thought it was interesting. And I was like, we're changing. Is that good? Why are we introducing complexity into a system? I thought that was really, really interesting. So this was an amazing chart. Okay, this chart, the person that wrote this, this was in the first chapter. The guy that wrote this, or the lady that wrote this, I forget. George M. Lowe wrote this. Do we know George Lowe? Is this good or bad? I don't know. I'm ignorant. That's good? Okay. You can tell how ignorant I am. This is great. I'm a third-party observer. I could leave, and you guys have to deal with what I said. All right, so George Lowe said this. This is how they planned out what missions they were going to do when. They said, too small a step would have involved the risk that is always inherent in manned spaceflight without any significant gain, without any real progress towards the lunar landing. Too large of a step, on the other hand, might have stretched the system beyond the capability and to the point where risk would have become excessive because the new requirements in flight operations were more than people could learn and practice and perfect in available time. Basically, you don't take baby steps. You take significant steps because you actually have to go towards the goal, and there will be risk involved, but you make sure that the risk isn't too big so that the engineers on the ground can't learn the lessons. I thought that was brilliant. So that's amazing. I've never read anything like that. I mean, I've worked on developing vehicles and active protection systems and counter missile systems. That was so succinct. It was amazing. And so then I looked at Artemis 3. To be clear, this is after Artemis 2, which is about to happen. So on Artemis 3, in order for this to work, like it starts up at the beginning, anyway, we've never done cryogenic refueling in orbit. Humans have not done that. Am I wrong about that? Somebody correct me. Am I wrong about that? Okay, let that sink in. Humans have never done cryogenic refueling in orbit up to this point right now. So make all the charts you want, but we need to take some steps. So I don't know how you guys are doing your programs, but I think this is very, very interesting. And I think it's important for you guys to talk about this with authority because you're smart and you know things. All right, don't get fixated on technology demonstration. Focus on the mission. Focus on the mission. Focus on the mission. I sound kind of arrogant right now, don't I? Please understand, I'm trying to be the voice of the 60s engineers. At least that's what I'm going to tell myself. So what is the mission? Some really cool people. Really, really cool people. These folks are awesome. If you've ever met any of them, you know they are legitimately awesome people. They really are. So my advice, and it's not my advice, it's through the generation of my grandfather, is keep it simple. As simple as you can make it and accomplish the mission That's what we should be doing. We should make it as simple as possible, okay? If you go through the old Apollo books, have you ever looked at how they decided to get the lunar lander off the moon, the ascent stage? It's crazy because it's awesome. They're like, all right, so we're gonna get the timing right. We're gonna launch. That doesn't work because things aren't whatevering. Here's what we're gonna do. You can read this in the stuff. They say, all right, if all else fails, here's what you do. Open the hatch, go around the back, and so there's these guillotines that connect the descent and the ascent stage, and you had to flip a switch, and it would cut the guillotines, right? They would cut them loose, and they would be disconnected and ready to hit the motor and go up. If that didn't work for whatever reason, they wrote a procedure. They're like, all right, here's the deal. Dude on the left or dude on the right, whoever has the best integrity of their suit at the time, the least amount of leaks, you're going to depressurize. You're going to get out of the spacecraft. You're going to go to the bottom of the spacecraft with bolt cutters. It's awesome. It's great. With bolt cutters, and you're going to cut the straps that are holding the ascent and the descent stage together. That's like the sixth thing down. Like they tried this. Okay, that worked. Oh, what if it doesn't work? Okay, we're going to go to this. Okay, then we're going to go to this. They had redundancy after redundancy after redundancy after redundancy, all the way down to the bolt cutters. And Harrison Schmitt said there was one thing after this. I just want to know what that was. Like, what is that? That's amazing. Are we building that level of redundancy into today's systems? Go look at the documents. This is a real thing. All right, so PID control loop. Positive and negative feedback is important. As the engineers responsible for getting humans to the moon safely and returning them, our friends, it is imperative that you provide negative feedback in situations that call for it, and you are not scared to do so. If you lose your job for providing negative feedback, good on you. If it needed to be said and nobody said it, that would be the worst thing to live with. So make sure you're speaking up. Be bold. Be courteous. Once a decision has been made, let's all get behind it and let's fight. But at the same time, let's be smart. Other things that we have the architecture we have. Let's make it work. I put some inspiring slides in there. All right, so you have a limited amount of time at this point to simplify. We've chosen the architecture. We know what we're going to do. There's a little bit of wiggle room right now, right? We've got some play. Not a lot, but we've got some play. So there are different things that you can choose and you can change. Make sure that you're making the right decisions. Focus on redundancy. Now I'm going to go back to this document. Everybody take a note. This is NASA SP287. This is your homework. If you do not read this document, I will think bad things about you until you do. There you go. There's a guy out there somewhere thinking bad things about you until you read this document. So some things I learned from this document that I'll paraphrase. Paraphrase is mine. Focus on redundancy. This is the ascent motor. Lots of valves do similar things. Really cool design. Tests are the key. This blew my mind. This chart's in here. They tested stuff, vibrational modes, right? Triaxial acceleration tests. They tested stuff and they shook it. You know what they found? 5% of the stuff broke because of how they did it. 1.5% on the left was due to the design of the component. 3.5% was workmanship, for a total of 5% of the stuff. This is just a representative of these stuff. But they explained why, and they're like, hey, there's going to be mishaps because we're humans and all the workmanship's not going to be perfect. You need to know it's there, you need to go find it. And the way you find it is test. I thought it was brilliant, man. This is an awesome document. Don't compromise on your standards. Let me tell you what's going to happen. I've given enough briefings at the Pentagon. Young engineers, if you haven't done that yet, you're going to do it, and this is what's going to happen. You're going to get in that room, and you're going to tell them, we can't do this, and we can't do this because of that. And they're going to say, but my schedule says this. And you're like, if you do this, then you just have to be willing to say the truth, okay? Sometimes the manager is going to accept the risk, and that's okay. You mitigate the risk as far as you can. You communicate clearly, but you make sure you don't compromise on standards. The one thing that always happened is people tried to figure out how to delete tests from the test plan. Always happens. oh man, we're 6 months behind. How do we gain that schedule? We delete that test that takes 8 months. Sometimes that's smart. And they did that in Apollo. After Apollo 8, they said in here that they were able to delete a couple of tests or a couple of shots. I forget what it was, but they saved a lot of time because there was one or two things they were able to mitigate the risk by cleverly designing experiments, and they saved time. It's really cool. Crew training is paramount. So I disagree with, I think I disagree with a lot of people on this one. So I think, and I made a video about this on Smarter Every Day, the Lunar Lander test vehicle, for example, if you're going to land in a 1/6 G environment, you have to know how to do that. Our pilots are used to walking around in 1G, okay? There's a weird thing that happens. A helicopter doesn't behave the same in 6G or 1G as it does in 1/6 G. So Neil Armstrong had a really, really interesting talk about this at the test pilot conference one time. Anyway, long story short, because of time, I found the engineer that helped design this thing, the Lunar Lander test vehicle. This is how they trained astronauts to land on the moon, okay? I think it's important. The reason this is more important than a simulator is the astronaut in the seat, their life is on the line. That matters. When your blood pressure goes up and it matters. I have to get this right. That psychological training has a huge component. So I spoke to a man named Mr. Ottinger, who worked on the control system, and I asked him a very important question. I said, well, I'll just let you hear it. Maybe I can get this right. Let's see what happens. But I would like to ask you two more questions, and these are big picture questions. So back in the day, the engineers and scientists on this program did amazing things with limited...
Analog electronics.
Right. He said analog electronics.
Do you think that engineers in the 50s and 60s were better than engineers today?
No. I think we all had our unique place in history, and they'll continue to be new challenges met, and there'll be innovation that continues. And part of it's because they can build on our shoulders. They can learn from what we did and then adapt to the new technology and so forth.
Do you think something like the LLTV needs to happen to train astronauts to go back to the moon?
They aren't going to go if they don't get a trainer, a free flight trainer, I can tell you that.
Really?
Yeah, they won't go without it. They know the value. They're smart enough to know.
Now the United States is planning to return to the moon.
It's Neil Armstrong.
The craft is on final approach to that flat-tip ridge near Shackleton Crater. I hope that the person at the controls has a simulation experience that is at least as good as the LLTV provided the Apollo crews a half-century later. Thank you.
I thought that was really interesting. The older generation believes in you. He said it. I said, do you think the Apollo engineers were smarter than engineers are today? I think a lot of us today, we kind of maybe think that about ourselves a little bit. Well, we got so many tools. We don't know how to do like differential equations like they did by hand. I think that. I don't know if you do. And so it was really encouraging to hear him say that. He said, no. And the way he said it was so interesting. No, we're not better than they are. It's different. And they're going to build on our shoulders. So here's the deal. There's a scoreboard. It exists. Apollo engineers, 6 lunar landings, Artemis 0. It's time to put points on the board. And they've given you the playbook. The playbook is called What Made Apollo a Success? SP287. I would encourage you to read it if you haven't. Yeah, we do not need to have an Apollo 1 type event in order to get us get us in gear. Don't get fixated on a technology demonstration. Just because we can do something new and sexy and awesome and amazing and wild doesn't mean you have to. Simple is good. And so as long as it accomplishes the mission. So be mission focused, and I think things are going to be okay. All right, so here's the thing that happens. Sometimes our thinking can get locked in on a thing. And it's like bias. We get biased on a thing. And so I'm going to tell you a story about how I got fixated on something. And so whatever you're doing in your job to get people back to the moon or Mars or whatever your job is, don't get fixated on the way people have told you it has to be. And this is why. So a long time ago, my buddy Barney, he's a welder. he said, "Hey, Destin, come on down to the weld shop." This was down at the missile range. Barney had built this bicycle. It's a really Dad, can I see that real quick? So Barney had taken a normal bicycle and he had flipped it around.
Check this out. Thanks. It's my dad. He's awesome. Yeah. So this bike it's really cool. It's like a transformer. Basically, this thing, when you turn the handlebar to the left, it goes to the right. Right? How many variables have I changed? Changed one variable. Does everybody in the room know how that thing works?
So it was really, really difficult for me to learn how to ride that thing. This is the first time I was on it. So the faster I go, the better. Yeah.
I couldn't do it. You can see that I'm laughing, but I'm actually really frustrated. In this moment, I had a really deep revelation. My thinking was in a rut. This bike revealed a very deep truth to me. I had the knowledge of how to operate the bike, but I did not have the understanding.
Okay, it's pretty interesting. Can one of you guys ride a bike? You can ride a bike? Can you help me for just a second? Yeah. All right. And what's your name?
Gabriel.
Gabriel, we don't have an SOP, we don't have PPE, we don't have anything. We're just gonna roll. All right, so here's what we're gonna do. Gabriel, I don't want you to hurt yourself. You're wearing a suit. It's a very nice looking suit. Do this. Go ahead and hop on this thing. Okay. And it's gonna do weird things to your brain, man, I promise. So just put your foot right there, and then just try to ride, let's say 1, 2, try to, look man, don't hurt yourself, okay? And go. Right?
Yeah.
You felt it, didn't you?
Yeah.
Nobody else in the room knows what it is. Try it again. Nobody else in the room knows how angry you are right now. I know. And go. Right? Isn't that crazy? What are you feeling?
I don't know. It's just like I go right and I try to turn right and it doesn't work.
Right? Thank you very much. Give it up for Gabriel. So what's happening right now is you've got this way of thinking that you've grown up your whole life learning this way of thinking. And it's just natural. This is what I do. This is how I do the TPS report. This is how I do the whatever, right? It's so hard. So I had to work to overcome my own brain at figuring this out. How long do you think it took me to learn how to ride this thing? Months. I did it for 5 minutes a day, and this is what that looks like when it finally worked.
One day I couldn't ride the bike, and the next day I could. It was like I could feel some kind of pathway in my brain that was now unlocked. It was really weird though. It's like there's this trail in my brain, but if I wasn't paying close enough attention to it, my brain would easily lose that neural path and jump back onto the old road it was more familiar with. Any small distractions at all, like a cell phone ringing in my pocket, would instantly throw my brain back to the old control algorithm and I would wreck. But at least I could ride it. My son is the closest person to me genetically, and he's been riding a normal bike for 3 years. That's over half his life. I wanted to know how long it would take him to learn how to ride a backwards bike, so I told him if he learned how to ride a backwards bike, he could go with me to Australia and meet a real astronaut. Are you gonna give up? Go ahead. This is how it starts. Look at this. This is such a big deal. Get up, you got it. Did you see his brain get it? So in how many weeks have we been doing this? 2 weeks? In 2 weeks, he did something that took me 8 months to do, which demonstrates that a child has more neuroplasticity, am I even saying that right, than an adult. It's clear from this experiment that children have a much more plastic brain than adults. That's why the best time to learn a language is when you're a young child.
So I have this like weird thing in my head where as I push off, I can like detect what's going on, and then my brain picks an algorithm and I can write it. For time, I'm just gonna fast forward to the next thing here. It's really interesting. Your brain gets in the way of your brain, that's the upshot.
So I only rode this for like 2 years. And the metaphor here is Apollo did a thing, and then we came along and we started doing our stuff, and we have the way we do things. And do you think we can just go back? So Amsterdam, I decided I'm gonna go to Amsterdam because I was over there doing test standards for missile stuff. And somebody's like, hey, let's go on a bike ride. I was like, yeah, bike ride to Amsterdam, that sounds amazing. I get on a bike and I cannot ride a bike. I straight up could not ride a bicycle. Like a 35-year-old man at the time here. And so what do you do? What do you do when you can't ride a bike in a city of more bicycles than people? you start trying to justify it, right? You're like, oh, no, yeah, I promise. So people were like crowding around and looking at me like, what's wrong with this American? Like a dude can't ride a bike. And so I got out my laptop and I started like showing these kids. I was like, no, here's a video of me riding a really weird bike, and that's why I can't do the normal bike, right? And this was really an interesting experience. And so the metaphor here is like, it's a simple bike. Like, it's literally rocket science. It's not simple. That didn't work at all. But we have the test plan. We know how to do it. But we've kind of got this other way that we're doing things. And the cool thing is you need to be able to do both. And so now what I can do is I went back and I learned how to ride the other bike. Nobody record what I'm about to show you. Nobody record this.
Okay, there's a cut in the video right here because I'm showing the crowd something that happened to me that's very interesting. It's a video and it involves another person that was on the street, and I don't have their permission to show it, so I don't want to show it publicly to the whole internet, but I do talk about it when I'm giving a talkie talk. So it's a really fun thing I do in person, but I don't think it's something I want to put on the whole internet. So anyway, it's hilarious too, and it drives home the point, which is why everybody's laughing when we go back into the footage here.
That's probably enough. So the point is, if you train for the unexpected, and they did that on Apollo. They had so many training plans they went through that everything that came up, like over 80% of the things that happened on orbit, they already had a procedure for it. And so the decision was automatic. And so the point is, when you're preparing for this stuff, you needed to train for the unexpected because you might even start surprising yourself. Everybody knows about the Apollo 12 lightning thing? Rad, right? What a great story, right? So you got to be ready for that stuff. So this is what I wanted when I would leave. I hope you would keep this with you. Look at the mission differently. Keep it simple, right? In a world of talkers, be a thinker and a doer. Be willing to take action. Feel free to take a picture of this if you want to. Be willing to take action in the meetings, to make the hard decisions, and ask the hard questions. Ask the hard questions. That's it. I'm Destin. I hope you enjoyed that, and I hope we're still friends.
I hope you enjoyed this video. I know this is a little different for the channel, but this was really fun for me and I thought you'd want to see it. I had to prepare and I was kind of intimidated by the subject matter, but it was a fun process and I thought you would enjoy checking this out. I'm grateful to the American Astronautical Society. There's a lot of smart people in this room and I'm just grateful to have been there. My point was simplify. Like we've chosen a very complicated architecture, and I think hopefully this video ages poorly. And Destin ends up looking like he cried wolf because he didn't understand or he wasn't smart enough to see the blah, blah, blah. I'm okay with that. Sometimes you just got to throw your hat in the ring and do the whole man in the arena thing. And that was what I was trying to do here. I decided to give this talk because I was seeing things and I felt like other people saw the things and they just weren't saying them. So I decided to say them. So I hope you would forgive me if I overstepped in any way, but I do think this is true. Also, I want to say thank you. If you're watching at this point in the video, thanks. I mean, you are emotionally supporting Smarter Every Day by giving me your time. I don't take that for granted. And I also want to thank the people that support on Patreon. I do this thing every year where I thank the people that stick with me by sending out stickers. So if you'd like to be a part of the sticker team or whatever you want to call it, you can support by going to patreon.com/smartereveryday. That's a really big deal when you elect to do that because it frees me from the algorithm. I can just make videos that are true to me and authentic, and that's what I want to do. So the sticker team, let me tell you how this went. Like back in the day, people were able to get this Supersonic Baseball team sticker and this James Webb Space Telescope team sticker. That is like, you can't get those anymore because those were people that supported on Patreon the last couple of years. Check out this year's sticker. It's the Smarter Every Day Exploration Team, and I love these stickers so much. It's my old helicopter helmet. And I think they're awesome. I spent a lot of time thinking about the size of the stickers because I want it to be just big enough where you might want to put it on a water bottle or, like a door or I don't know, something like that, like a laptop. but not too big that it's just overwhelming whatever you're putting it on. So I spent a lot of time thinking about the size of these stickers. I hope you like it. I've got a little bonus sticker I'm going to put in there too. I'm not going to tell you what that one is. But to everybody that supports on Patreon at patreon.com/smartereveryday, this is my way of saying thank you for sticking with me. And of course, if you've just now started supporting, I'm going to send you the baseball as well. Patreon.com/smartereveryday. I'm so grateful that you would consider doing that, because my goal is making authentic content on the internet, while all the while like pushing off the increasing pressure to make sensational content. That's not what I want to do. So thank you so much for considering that. That's patreon.com/smartereveryday. That's it. I hope you enjoyed this video. Thank you for emotionally supporting me. I'm grateful. I don't take it for granted. That's it. I'm Destin. You're getting smarter every day. Have a good one.